Introduction to lasers. At the end of this lesson, you will be able to define the characteristics of laser on comparison with ordinary light. Explain the basic principle and conditions for working of laser. Explain absorption, spontaneous and stimulated emission in a two-level system. List the properties of laser. The fear for darkness vanished when man discovered fire. Till then, man knew only the natural sources of light. Later, light source evolved into different artificial forms. Physicists had worked to create devices for producing powerful beam of light. This resulted in the invention of lasers. Lasers are an important milestone in the field of engineering and science. From a barcode scanner to intruder detection in high security areas. From a projection pointer to printers. From optical tweezers for handling delicate matter to cutting off high-strength materials. From removing body art to complicated eye surgery, lasers are simply everywhere. Lasers have unique characteristics differing from ordinary light. This enables to produce highly intense light focused to a small point. Next, let us discuss the basic principles, characteristics, and working of a laser. The term laser is an acronym of light amplification by stimulated emission of radiation. It is a device which produces an intense beam of monochromatic and coherent light. Every invention has some history, so indeed lasers. The basic principle of laser is based on the Einstein's theory of light proposed in 1916, which was later developed by Gordon Gould in 1957. In 1960, Theodore Mayman invented the first working ruby laser, which was also the first optical laser. Apart from solids such as ruby, researchers have analyzed that some materials like xenon, helium, or semiconductors can also be used as laser mediums. Different types of lasers have been developed, which enhanced the scope of their applications. The working and principle of the laser is based on some important features. Let us discuss about them. The working principle of lasers is based on spontaneous absorption, spontaneous emission, stimulated emission, and population inversion. Absorption. An atom consists of different energy states. Let us consider two different states of an electron, such as ground state, E0, and excited state, EX. Electromagnetic energy falls on an atom in the form of photon of frequency F. From the principle of conservation of energy, the electromagnetic energy is given as the difference of EX and E0. When the photon energy falls on the electron, it jumps from the ground E0 to the excited state EX by absorbing the energy. This process of absorbing energy from photons is known as absorption of radiation. Spontaneous emission. It is known that electron absorbs energy and moves from lower energy level E0 to the higher energy level EX. But the excited electrons that had jumped to the higher energy state does not remain in the same state for a long period and comes back to its original ground state E0 by losing its energy in the form of photons. These photons are considered as incoherent light as they do have any correlation in phase. Thus, the electrons in the excited atoms are released on their own from their higher energy state to the ground state, emitting photons. This is called as spontaneous emission. The mean life or lifetime of the excited atom is the time for which it stays in that state. This is about 10 to the power minus 8 seconds before spontaneous emission. However, The mean life for some excited states is 10 to the power 5 times longer, and such states are called as metastable state, and they play an important role in laser operation. Stimulated emission. In this process, the atom is initially present in its excited state EX. A photon of energy HF can stimulate the atom to move to its ground state E0. During this process, the atom emits an additional photon with the same energy HF. This process is called as stimulated emission as it is triggered by an external photon. Population inversion. Generally, in any atomic system, the number of atoms in the ground state is more than that in the excited state. This is because of the tendency of electrons to stay in the ground state. But in order for more photons to be emitted, there should be more electrons in the excited state. This process is achieved through optical pumping, and this occurrence is known as population inversion. The transition electrons do not stay in an excited state for a longer time, but in some systems, the electrons remain in an excited state for a longer period. These systems are called as active systems or media. Generally, these active systems are compounds or mixtures of different elements. Consider the active system containing a large number of atoms in thermal equilibrium condition at a temperature T. Before the system is subjected to any radiation, there are N0 number of atoms present in their ground state with energy E0, and a number Nx are in a state of higher energy Ex. According to Ludwig Boltzmann, Nx can be given in terms of N0. Nx is equal to N0 into e to the power of minus of Ex minus E0 divided by kT. As the temperature increases due to thermal agitation, more number of atoms move to the higher energy state Ex. Since Ex is greater than E0, the Boltzmann equation requires Nx to be lesser than N0, means there will be less number of atoms in the excited state compared to the ground state. Thus, only by thermal agitation, the populations of Ex can exceed that of E0. Suppose the atoms are flooded with the photons of energy Ex minus E0. Then, by absorption by ground state atoms, the photons will disappear and atoms move to excited state, leading to population inversion. Thus, through stimulated emission of excited state atoms, more number of photons will be generated. Einstein showed that the probabilities per atom for absorption and stimulated emission processes are identical. Thus, the net effect will be absorption of photons when more atoms are in the ground state. When stimulated emission dominates, that is, when more photons are emitted than the absorbed photons, the laser light is produced. The lasers have certain unique characteristics that enable the laser light to be focused 100 times better than the ordinary light. These characteristics are monochromaticity, coherence, directionality, and sharp focus. Let us discuss these in detail. Laser lights are highly monochromatic. It means the laser beam is made up of a single color or a single wavelength. In contrast, the ordinary white light from an incandescent light bulb is a combination of many colors or wavelengths and is certainly not monochromatic. The laser is highly coherent, means the wavelength of the laser light is in phase in space and time. This is because of the orderly electronic transitions that take place in laser. The laser light can travel several hundred kilometers long in space without any destruction, whereas the corresponding coherence length for wave trains emitted by ordinary light is typically less than a meter. Laser emits light that are highly directional, which means the light emitted by the laser are relatively a narrow beam in a specific direction without dispersion. Moreover, the laser beam spreads very little and thus can be focused sharply. But if you observe the ordinary light bulb, it emits light in many directions away from the source. Thus, lasers with the unique characteristics illuminate, investigate, repair, transfer, cure, and detect. Certainly, it is interesting to know about the fundamentals of laser technology. As always, you could connect it in some form of application in day-to-day life. In this lesson, we have learned laser or light amplification by stimulated emission of radiation is a device which produces an intense beam of monochromatic light. The working of lasers is based on absorption, spontaneous emission, stimulated emission, and population inversion. The important characteristics of lasers are monochromaticity, coherence, directionality, and sharp.